Dror has come in and has offered to talk about some compressive sensing, which looks at can you get reconstructions or get additional information and compression by doing projections and simplify the sensing process.
Yeah, so first, thanks to Michelle for inviting me over. And I was telling Michelle several minutes ago that it is an honor to be giving a talk at Google because I've given talks at different companies before, but Google's the first company that I'm giving a talk at. And I actually use your products. I use Google Mail. I obviously use your browser. I obviously use your search engine. So this is entertaining. Now my talk is really going to be about compressed sensing that, as Michelle just mentioned, deals with acquiring signals from a reduced number of measurements. And my special angle is an information theory angle, where that was my traditional type of background. I've also done signal processing, machine learning, developed hardware in the late 90s, so I have a varied background. But I saw that a lot of ideas from information theory could be useful for compressed sensing. And in 2005, I started bringing in some of these ideas. Before I begin, I first of all want to thank all of my collaborators on this work. Deanna, who is sitting here, is a collaborator on an upcoming paper. And additionally, I want to mention that you're invited to interrupt me at any time. So let us begin. I think that there's no need in this forum to say that sensing, computation, and communication have had a radical impact on our society over the last several decades. And that's because these technologies are fast, readily available, and cheap. Now, there's been a lot of progress in individual disciplines that many of you guys were telling me that you work on, and you ladies. Signal processing, communications, networks. Obviously, computation is a strong side at Google. But nowadays, we're really faced with new types of challenges. We have data that is really streaming at us from all types of different directions. Audio data, image data, video data, financial data. I was at a hedge fund for a year and a half. Seismic data, you name it. And the data acquisition is actually being performed on a global scale, massive amounts of data. We want to process that. And at the same time, our analysis is being hampered by Moore's law, which is kind of slowing down. It used to be that every 2 years the clock rates were doubling. That's not really the situation anymore. So we have a lot of challenges. But I want to discuss the opportunities. And I think that, what is that?
Could you mute your mic? Thanks.
I want to discuss the opportunities. And I think that our planet, there's a lot of beauty on our planet. And if we look around and we try to find constructive solutions, there are numerous contributions that we can make. And the contribution that I'm going to discuss today is compressed sensing, which is really a new way of how to acquire signals. Now, if you think about the old-fashioned way that signal processing works, you have this analog data. That's the input. It could be a picture, and you used to have a camera, and you would be sampling the analog data. And as long as you sample fast enough at the Nyquist frequency, which is twice the highest analog frequency in the data, then these n numbers suffice to later do anything you want, reconstruct the input perfectly. Now, of course, n numbers could be quite a lot. We want to transmit from the encoding side to the decoding side much less information. We want to compress. And a compression algorithm in many signal processing applications really means that we take these n numbers, you can think of it as a long vector, and you compute inner products relative to some basis vectors in which the data happens to be sparse. Most of the numbers will be very small. A few of them will be big. And we're going to keep the k largest ones, transmit them, and that's the whole encoder. Now, the receiver or decoder side, it takes those k numbers and it forms a linear combination of the k relevant basis vectors, and that gives us the approximation x hat to the input x. And you'll note something interesting here. There's a lot of stuff happening on the encoder side, while the receiver is actually very simple. You have this, first of all, this sampler. And whereas Moore's law, in the past at least, clocks were doubling every 2 years or so, in analog to digital converters, clocks are doubling every 6 years. And they are simply not fast enough in many applications. Another challenge is on the compression side, a lot of computation. And of course, I don't need to tell you that oftentimes the encoder is actually a battery-operated device, such as this. And we want that to consume as little power as possible, be fast, etc. And nonetheless, this paradigm has worked for decades, this DSP, digital signal processing paradigm. And that is because many types of data are indeed sparse. You'll take a look at this picture from MIT. And here are the appropriate corresponding wavelet coefficients. And you'll see that most of them are dark blue. Now, what are these wavelet coefficients? Here, you'll see the subbands with the higher temporal, spatiotemporal frequencies. And these subbands contain the high frequency information, the details, and most of them are dark blue. Dark blue means close to 0, small amplitude. Now, at the lower frequencies, you have a lot of information, bright colors, red, yellow. And you'll notice that most of the information here is really focused in a small number of coefficients. So we took a very large number of pixels, n, and we translated it down to k numbers. It's, of course, not only images, it's also video, which Michelle deals with. It's also acoustic data. This bat, it's chirping, and a chirp may sound something like whoop. And in the time domain, the x-axis is time, the y-axis is the signal itself. And you can see that the signal is pretty wild. You would need to sample it pretty rapidly. But when we try to represent this in an appropriately chosen Gabor basis, all of a sudden the x-axis is time, the y-axis is now instantaneous frequency. And that bat chirp at any point of time is dominated by 2 or 3 frequencies. Very sparse. Now, if you think about the Nyquist or Shannon sampling theorem, that theorem is telling you you have the highest analog frequency in the data. And you need to sample at twice the highest frequency in order to later process your input. But the thing is that this is a worst case bound for the very large class of all band-limited signals. And it so happens that for many signals of interest, as I just mentioned, we have more information. We have sparsity. And ideally, what we would like to do is to directly sense the compressible information at a much reduced measurement rate. And that's where compressed sensing comes in. Emmanuel Candes and David Donahoe, they showed that sparse signals can be recovered, sometimes perfectly, from a small number of linear measurements. There's been a lot of additional research since their earlier works in 2004, 2005. And the idea is perhaps a bit startling. You take your analog input x, and you take projections, inner products, relative to basis vectors that are white noise. So random projections. And I'll tell you later how this can actually be performed in analog in some systems. At Google, you are probably interested in digital types of random projections, and we will discuss that later. But all you really need to do is take these m random projections in analog. Each of these random projections is kind of like a sufficient statistic. In my information theoretic terminology, I think of it as a few bits of information. And if you have enough of these random projections, enough, the number of measurements m needs to be mildly larger than k, the number of big numbers that we're interested in. If you're, let's say, 4 or 5k measurements, you often have enough information to recover the signal quite well. So the encoder side is very simple. All it does is takes these random projections in analog, or perhaps in Google's case, in digital. The receiver side, in contrast, must be aware of the basis in which your data happens to be sparse. And you run an optimization routine, and that's what I call the decoder. And this optimization routine could be computationally intense. And we've moved the action. In the traditional DSP paradigm, it was happening in the encoder. And in the compressed sensing paradigm, we've moved it toward the decoder. Now, let's give a bit more details. The compressed sensing encoding, and I'll start introducing my notation. I have a column vector x, and it's of length n. N could be a large number. But it's a sparse column. To keep things as simple as possible for right now, I'm going to assume that these blue boxes, k blue boxes, are non-zero, and the rest of it is 0. This is, of course, a simplification. And I'm taking inner product. So each of these rows of the matrix phi, I compute an inner product between the row and the column vector x, and that's one inner product, one measurement. And I accumulate these inner products into the measurement matrix phi. And the matrix vector product, phi times x, gives me the measurement vector y. And once again, I have m measurements, and m is mildly larger than k. Now, for emphasis, random projections. And the random projections are interesting because no matter what basis you happen to be sparse in, you will still get several bits of information from each of these measurements. And this leads to the concept of universality. Universality to any basis vector in which you happen to be sparse. I'd like to illustrate that you can actually take these things in analog. This is, has anybody of you in the room seen this slide? OK, so nobody. Well, I know that one person has, but she's very modest. This is what we call at Rice University, when I was a postdoc there in 2006, the single pixel camera. If you think of that projector, perhaps not that one, but many projectors nowadays, the way how they work, you have a light bulb, and it's reflecting light, which is bouncing off an array of really tiny micromirrors. And that array of micromirrors is being controlled. Each micromirror is pointing in a different direction. And by controlling their orientations, we control what amount of light gets to the screen. We're doing something which is analogous to that, but kind of dual. We're taking light from an outside screen, an outside scene, I apologize, and we are bouncing light off an array of mirrors onto a single photodiode. And of course, we need some lenses in between and that hardware type of stuff. Now, by controlling the orientations of the mirrors, I control whether photons from a pixel in the outside scene reaches my photodiode or not. And that basically means that I am adding up photons in the optical domain. This is an inner product, an optical inner product in analog. And that's all we do. We take that photodiode, analog to digital converter. That is our entire encoder. OK? Now, of course, the receiver side, the decoder, has a lot of signal processing in it, optimization routines. That's where the hard work is. But these are random projections in analog. And I want to emphasize a single photodiode. So the thing that I have in my pocket, which by chance does not have a camera on it, but many of you do have these things in your pockets with cameras on them, they have these million-pixel cameras. And they're cheap. They're cheap because silicon happens to be sensitive to light at the waveforms that are interesting to us. So you can build these $2, $3 chips with 1 million pixels, 1 million CCDs. But suppose that you're interested in some other type of light, like X-rays or whatever. And each pixel, each sensor would cost you $1,000. How are you ever going to build a 1 million pixel camera where each pixel costs $1,000? Now, maybe at Google you have those budgets. Maybe the defense agencies have those budgets. But very few people, very few applications can build that type of camera. And here we use one photodiode. To give you an idea that this kind of works, here is a 64 by 64 image of the letter R, 4,096 pixels. And you also see a 400 wavelet term approximation, which is pretty good. And when we took our compressed sensing system with 1,600 measurements, and 1,600 is 38% of the number of pixels, so the number of measurements was greatly reduced, this is what we got. Now, it looks pretty fuzzy. But the fuzziness is actually not because our math is mistaken. The fuzziness is because if you put a real ordinary camera at the light plane of where our micromirror array was, this is what you got, a very, very fuzzy thing. So the hardware was off. And later on, after I was no longer a postdoc there, they improved the camera. It performs a bit better. But the main take-home point is you can actually take these things in analog. I would also like to mention not only the encoder, but also the decoder side. The problem is as follows. We have this long vector x, and we're measuring it with a matrix that has far fewer rows than columns. And the resulting measurements, y, this is basically an underdetermined system. We cannot give a unique solution. There are infinitely many solutions. We have an entire subspace of possible solutions to this linear system. This is an ill-posed problem. OK, what do? Well, we know that x is sparse. So intuitively, what we do, we search within the subspace of explanations for the most likely explanation. And the notion of likelihood can account for the types of priors, the types of information that we have about our input x. Now, the contribution by people such as Candes and Donahoe earlier in around 2005 was that linear program decoding can work very well from a modest number of these measurements. In some cases, actually, you can get perfect reconstruction if the measurements are noiseless. And additionally, linear programs are, of course, computationally tractable, polynomial complexity. After these initial discoveries, there were variations along this reconstruction theme. My co-author, Diedo Needle, for example, who is with us here, Joel Trapp, who is at Caltech probably at the moment, they did greedy types of algorithms. Other optimization approaches were also performed. There has been progress. I will tell you about more later. But the real picture is that compressed sensing changes the rules of the data acquisition game. Instead of sampling at the Nyquist rate, you can take far fewer measurements. Now, on the hardware and software side, we have this beautiful notion of universality. No matter what basis you happen to be sparse in, if you know that basis, those sufficient statistics will allow you to reconstruct. And this universality really simplifies the design of both the hardware and the algorithms. Now, on the mathematical side, because we have a sufficient statistic from each of these measurements, and the bits kind of add up, if you have very few measurements, you can get very little information. And you can do simple stuff like detection and recognition. If you have a lot of measurements, a lot of bits, you can reconstruct your original input quite well. And these types of ideas, in our opinion, might fuel the next generation of signal acquisition devices. I've already told you about new imaging devices. I will not mention distributed source coding algorithms today. I might take that offline with some of you who might be particularly interested in video coding. And I will discuss other types of topics. And my emphasis is on how information theory inspires compressed sensing. And I'd like to pause and also mention that I believe that at Google you are aware that there are many types of measurement systems that are linear. We have this y equals phi x, possibly plus noise type of problem. This appears in many areas of science and engineering. I will emphasize one of them later on. And you need to think about this is not just compressed sensing. These principles will appear in other areas. And I'm going to begin by talking about information theoretic bounds, some earlier work from 2006 with Sarvutam and Baranuk, and very recent work from last week with Dongnyung Duo from Northwestern University and Shlomo Shammai in Israel. So originally, our target here in compressed sensing is to reduce the consumption of resources. Measurements are a resource. It can be the rate of an analog to digital converter, or it could be power, or it could be the cost of the hardware, resources. And this motivated David Donahoe to write several years ago, why go to so much effort to acquire all the data, those n numbers, if when most of what we get will be thrown away? We only are interested in those k large numbers. All the rest is going to be thrown away. Now, let us start adding complexity into our model. Our model considers a signal entry, xn, that is the nth location in x, this yellow box. And that location is a product of two things. Bn, which is a Bernoulli random variable, probability epsilon of being 1, small probability of being 1. And the rest of the time it's 0, so you have these white boxes which are zeros. And you multiply that by un. Un follows some distribution, pu. There are some minor technical conditions. And the product of the two gives us this yellow box. Now, because u can take various values, it can be, again, minor technical conditions, any PDF that you want, instead of blue boxes, we have colored boxes. So we've made this a bit more interesting. And you'll note that the distribution of px because the Bernoulli has a high probability of being 0, I have this delta at the origin of the PDF for x, and I have, with small probability, pu, and that small probability is reflected in the smaller amplitude. And I'd also like to mention that epsilon could actually be 1. And in that case, xn is equal to un, and we have a completely non-sparse colored input. We can do this. Our math can do this. And an issue which is crucial to understand is that typically in most compressed sensing systems, maybe not the ones that you're interested in at Google per se, but most systems will be analog. And analog systems, I've designed hardware in the 90s, in the late 90s. Analog systems have a lot of problems. We have measurement noise. We have nonlinearities. We have crosstalk between wires. I've seen these things on oscilloscopes with my own eyes. It's a very messy problem. And consequently, for ease of analysis, we are going to assume in our analysis Gaussian noise. And nonetheless, these results can be generalized to other noise distributions. So one step further in complicating my problem, I have this matrix times vector phi x. Instead of calling that y, I now call it y0, the noiseless portion of the measurements, and I multiply it by the square root of gamma. I'll soon tell you what gamma actually means. And I have the noise. I add a additive white Gaussian noise vector, unit norm, 0 variance, and that is the vector z. And if you think about it, it can easily be shown that as long as the columns of the matrix have unit norm on average, this might be a random matrix. As long as they have unit norm, then the signal-to-noise ratio of each of these measurements will be gamma. That's the operational meaning of gamma. Now, in 2006, I showed the following result. I had this insight that you have the noiseless measurements y0, and they're being corrupted by noise. And that means that at the output, you have y. And this is, in information theory, a channel. Now, what is the multiplication by the vector phi? This matrix vector multiplication is a type of encoder, a compression algorithm. In information theory, we say that we compress the source, and then we apply another code to protect against corruptions of the channel. The compressed sensing measurement, the matrix vector multiplication, is nothing other than these two encoders. The compressed sensing reconstruction algorithm, or decoder, is nothing other than redoing the channel code and redoing the source code. Compressed sensing is a communication system. And this led me to understanding that we have a measurement channel, and each of the measurements is providing me some additional information about my input. The more measurements, the more information. And that led to a very simple bound on the number of measurements required. So consider a sparse signal x, and its rate distortion function is r and d. I'm soon going to explain what that means, r of d. We want to achieve distortion d. It can be any distortion metric that you want. Mean square error, mean absolute square error, polka dots, whatever, okay? D, distortion metric. And we want to operate with signal-to-noise ratio gamma. And what we're really interested in is a bound on how many measurements we need. We use the limit where the number of measurements, m, and the length of the input, n, they're both blowing up to infinity together, but the ratio is held constant, delta. And delta will be positive in most problems of interest. And this is the bound. In the numerator, we have the rate distortion function. R of d means the number of bits per input element that are required to achieve distortion d. In the denominator, we have the number of bits that each measurement gives us, the capacity of the channel. Very, very simple result. Based on this early single-letter expression, a single-letter expression in information theory parlance means you blow up the size of the problem. M and n go to infinity together with the same ratio. Everything scales up. Based on this single-letter bound, there were other authors with similar single letter bounds. And I've listed quite a few, but there are many more papers. But these are all bounds. And our goal with Dangmin Guo and Shlomo Shammai was to give a precise characterization, not a bound, but a precise characterization of optimal compressed sensing. Optimal in the sense of the ultimate performance. Now, we have these n numbers entering our system. The matrix vector multiplication and the channel noise. Let's just think about that as...
Excuse me, a question?
Yes, Mutu.
Can you go back to the previous slide? I'm sorry, the slide one before this. Yeah. Can you just help us understand this with respect to either known results in information theory? Not this one, the one next to it. The theorem, the main result.
This one. Yes. So this is basically, in information theory, there's a very well-known theorem called source channel separation. To put things as informally as possible, it means if you give me 1,000 bits and each measurement, each usage of the channel gives me 2 bits and you need 1,000 bits, then we need 500 measurements. Okay? That's a very well-known theorem. Does that help address your concern?
Well, I have 2 questions. One is, in what form is this particular theorem different from what you do in signal processing and information theory? And second, how does this relate to compressed sensing?
This is completely a trivial result in information theory. In information theory, the whole contribution was to set up, in the previous slide, to explain that compressed sensing was actually a communication system. That was my contribution, this model over here. The theorem is trivial for the information theory community. Now, from the compressed sensing angle, on the other hand, the contribution is we finally have, or had in 2006, a very early and coarse bound on the measurement rate required. Okay?
I have a question about that.
Yes.
What does the term single letter refer to?
Okay, single letter means that we want one term that as we blow up the size of the input, n goes to infinity, we have one expression R of d that tells you how many bits you need per input element to achieve distortion per element of d. So the distortion will be proportional to n, and the number of bits will be proportional to n. But this single letter expression means that everything, both the amount of distortion and the number of bits, will be going linearly, growing linearly together, okay? Does that clarify things? More questions?
It means like a block.
Excuse me?
In block coding, it's like
Yes, yes.
A single letter is like a block.
No. The single letter is basically the limiting performance of how many, in my specific case of R of d, how many bits per input, per entry, per number in the input of that, every box of that long vector x, okay? How many bits to achieve distortion d for that one block?
So it's one variable problem size description.
Yes, yes.
So
More?
say pick your ratios and fix those, and then the problem size is described by one variable.
Okay.
Okay, so there were earlier bounds. We wanted to give a characterization, a precise characterization. And we have this input of length n, and the measurement matrix and the noise, think about it just as your channel.
Sorry.
Yes, Mutu.
We're still trying to figure this out. So I still want to go back to my 2 questions. One is, for me, compressed sensing is simply not the, if you're defining compressed sensing as simply the number of bits needed to measure a signal, then it doesn't have the other properties like universality or arbitrary basis. So can you comment on sort of what part of compressed sensing is directly just channel compression?
It is assumed here that you know the measurement matrix, and it is assumed here that you know the basis in which the data happen to be sparse. Under these assumptions, that is expression. Okay, so those are assumed to be known, okay? So you know the measurement matrix. You know the basis in which you happen to be sparse. You know the noisy measurements y, and given them, you want to reconstruct x. Is this clear? Okay, wonderful.
Okay, good. Enough?
Okay, so given this measurement channel, including the matrix vector product, we then have the noisy measurements. We are given, just as Mutu asked, we are given the measurement matrix phi and the sparsifying basis, and given the data, the noisy measurements, we ideally would like a posterior to enable us to estimate this nth location, xn. And our estimate will be called xn tag. We want to know, ideally, ultimately, we would like to understand what can be said about that nth location, the quality of our estimate, xn prime, given the noisy measurements and the matrix. Now, ideally, if we could compute the posterior, that would be a sufficient statistic for everything that you want to know. Minimum mean square error, absolute error, getting the support set exactly right if the signal happens to be precisely sparse. Anything that you wanted to know, this would be a sufficient statistic. But this is a problem of n dimensions, and it is very complicated computationally to compute the posterior. Not going to happen, especially when n blows up to infinity. Now, what we want is a very simple characterization of how the posterior looks and the quality of these metrics, how well we can basically reconstruct using different performance metrics. And we were approaching this problem using a large system limit where, once again, m and n, number of measurements, length of the input, blow up to infinity, and the ratio is held constant and, of course, positive for problems of practical interest. And now this is the main slide. On the one hand, you have this system, this entire vector, and you have this big channel, and you have the posterior. And we would like to estimate xn prime, xn tag. On the other hand, you have this scalar description. One input goes through some channel, goes into z. Then we have a posterior, and we estimate x prime. Now, suppose that a genie told you everything else about the input except for xn. You were trying to estimate the nth location given information on everything else. So basically, you could subtract off everything else, and you would be having one column of the matrix times that nth location plus noise. And of course, you would be multiplying by square root of gamma, and you would have this single number times square root of gamma plus unit norm Gaussian noise. And the posterior would be very clear. This is a scalar Gaussian channel. One input, one output, very clear. What we've shown formally is that when you do not know these other guys, you do not know the rest of the input. It so happens that each of them, you reconstruct it with some error term, of course. It's going to be a noisy reconstruction in practice when we have measurement noise and a finite number of measurements. And each of these, we will be subtracting them off, but with noise. And the accumulation of all these noises, intuitively, this is kind of like the central limit theorem. We will have additional Gaussian noise added into the problem. And one way of thinking about it is I will be multiplying by the same square root of gamma and adding Gaussian noise with higher variance. Another way of thinking about it, the way how we present our results, is we multiply by square root of gamma times eta, where eta is less than 1. So we are multiplying by less, and then we're adding our unit norm Gaussian noise. And that is the entire posterior in the large system limit. Basically, the bottom line is that estimation quality, given the noisy measurements y and the measurement matrix phi, will be just as good as a noisier scalar observation. And an important point here is that eta, the degradation term, can be easily, so to speak, in quotation marks, computed. How easily? Well, we have this fixed point expression, and when you solve it, where the MMSC is basically the minimum mean square error for some random variable that appears in this problem, this thing can be solved in 1 second. Okay, I mean this is trivial. Okay, we can compute the degradation, and the real take-home point, once again, a scalar posterior. The posterior looks just like a scalar, Gaussian, noisy observation, but degraded with more Gaussian noise. Now, I must admit some, caveats here. our analysis is not truly rigorous because we're relying on the replica method, which is widely accepted in statistical physics. We're using a symmetry assumption. And these types of assumptions, they've been validated numerically to be almost precise in various communities. But nonetheless, these are assumptions and perhaps not exactly precise. And they've been used for CDMA detection as early as 2002 by Tanaka and by my co-author Dongning Guo and his PhD advisor Sergio Verdu later on in 2005. So this is not a theorem, it's a claim based on well-established results. That's one caveat. I also want to mention that there has been a very interesting recent analysis by Rangan et al. And what they did, they took that paper by Guo and Verdu, and based on that, they showed the minimum mean square error estimator quality. Not the posterior, but this minimum mean square error. As I mentioned earlier, the posterior enables us to give you any metric that you want. The posterior is a sufficient statistic. Additionally, what they did, which is very interesting, they extended the analysis of Guo and Verdu to additional compressed sensing algorithms, and particularly the lasso, which I'm assuming that many of you are familiar with in the machine learning community. Now, another result that we have, that was result number 1, decoupling. And I'll take this a bit quickly. You basically have a fixed number L of locations in your input. And your input is becoming longer and longer, but a fixed number L of locations. And you're asking not just the posterior of xn, but the posterior of L locations, L fixed locations. Now this is a posterior given the noisy observations y and the measurement matrix phi. And you'll note that in our problem, in our setting, y and phi are themselves random. So this is a posterior of something random. This is a complicated beast. But it turns out that as you scale up the size of the problem, this complicated beast takes the form of a product, and once again, convergence in distribution in the large system limit to a product of L scalar degraded Gaussian observations. And once again, we have a take-home point here. The individual posteriors, we have L, a fixed number. The individual posteriors are asymptotically independent. The interference in location number 1 does not really matter much when you look at location number 2. And I will demonstrate this graphically later. We have great interest in sparse measurement matrices. And that interest arises because the old-fashioned way of doing compressed sensing with these dense Gaussian matrices, a lot of people studied, these matrices, because they are dense, the matrix vector product requires a lot of computation. And in contrast, we considered a sparse measurement matrix. We were inspired once again by low-density parity check codes, which have been used in the information theory community. And we have mostly zeros in our phi matrix. The phi matrix mostly consists of white 0 boxes, but a few red boxes. We have probability Q of having any single red box. And given that you have a red box, we have a distribution, P phi, for that red box. Once again, minor technical conditions. Q needs to be not too small, not too big. As the size of the problem grows to infinity, Q can become very, very small. So this will be a very sparse matrix as we scale things up. But the conditions are not too stringent. And the bottom line here is that each row will, on average, contain n times Q of these red boxes. And because of that, all of a sudden, the matrix vector product is very rapid. And this gives us fast encoding and decoding. Now in 2006, with Sarvatam and Baranuk, we started thinking about using belief propagation to solve this problem. Belief propagation, once again, is well known from the information theoretic community. I was speaking with Michelle earlier, and she's very familiar. And we represent the measurement matrix by a bipartite graph, which you can see. On one side of the bipartite graph, you have the measurements y, the noisy measurements. And on the other side, you have x, the input, which we are attempting to reconstruct. Now what we're doing, we are estimating the real valued input iteratively by passing messages back and forth from the measurements to our estimates of the posterior, back to the measurements, and so on. And gradually this converges. And we take into account our statistical familiarity of, first of all, the input, and secondly, the noise. Our specific implementation relies on non-parametric belief propagation. That is belief propagation for real numbers. Several people, quite a few people, have been working on that recently. This is, again, an active area of research. My collaborator, Danny Bixson, Sommer, Feder, and Shalvi have another very interesting paper from last year, active area. Now, why am I mentioning these sparse matrices? Because it so happens that under those mild technical conditions, the same result as before. Degraded observations with the same degradation eta. Identical. Mild conditions on the degree of sparsity. Not too sparse, but just sparse enough. So sparse matrices are good. And additionally, and this is actually a theorem. This no longer relies on these replica method assumptions. Theorem proof, belief propagation is asymptotically optimal for sparse measurement matrices. So you should definitely, if you have the ability at Google to choose your measurement matrix, use a sparse one, and belief propagation will give you the best reconstruction that money will buy. And let us now use the belief propagation to illustrate some of these results. First of all, decoupling. I have two axes here. This is the posterior for the second entry of the input, and this is the posterior of the first entry of the input. I had an input, the vector x, of length 500, and I took this input. In the first two entries, it was a Bernoulli input, ones and zeros. The first two, I fixed them to 1. For a problem of length 500, fixing them 2 locations to 1 doesn't really change much, because 10% of the numbers are 1s. So changing 2 doesn't really matter much, doesn't really change the statistics by much. And if you think about it, well, of course we would like to estimate a 1 for both of these locations. But regardless of the posterior that was estimated for the second entry of the signal, the posterior for the first entry has this same type of form. You can see the flatness of the surface, where the vertical axis is the density. The density meaning a histogram over thousands of simulations of this length 500 problem. Okay? Now, if you look at this histogram, this density, putting aside the decoupling, you'll see that most of the time it's pretty high. It's near 1. So most of the time the algorithm thinks, oh yeah, it's close to 1. It's probably 1 if we were forced to make a hard decision. Sometimes the algorithm makes a mistake and it thinks that it's probably 0. Next, I want to illustrate the performance of belief propagation compared to other algorithms. On the x-axis, we have the number of measurements, which begins by 100 and went up to approximately 800. This is for a problem, an input of length 1,000. My input was not Bernoulli, but it was a 2-component mixture Gaussian. Okay, so this is a more realistic input. And the y-axis is the minimum mean square error. Now clearly, the x-axis, the number of measurements, when you have more measurements, you improve your error. This is obvious to everybody. What I want to illustrate here is that compressed sensing via belief propagation actually works. And we have these various curves. And these various curves are different algorithms. Of course, more measurements, better performance, lower square error. And these curves include iterative hard thresholding, which is very fast. You'll see that soon. Cosamp, which is Deanna's algorithm. It's also quite fast. It's a greedy algorithm. These two are related algorithms. That's why their performance is similar. We have the original linear program, which was the innovation of compressed sensing. And we have GPSR, which is an implementation, a fast implementation of the lasso. And the lasso is a relative of linear programs. They happen to be slightly better. Belief propagation, the red line, you can see that it's clearly better. Of course it's better because it's asymptotically optimal. When we wrote the paper about belief propagation, we had no idea. This result is from the last, we became aware of this very recently. But belief propagation will give you the best reconstruction that money will buy if you're allowed to use sparse matrices. How fast is it? Well, the belief propagation is n poly log n, square of log n. And I took a problem where I am varying the length of the input n, and I fixed the number of measurements as 40% of n. And I'm comparing different algorithms where the x-axis is the length of the input n, and the y, the vertical axis, is the time in seconds that it took to run the algorithm. And you'll note, first of all, that this very sharp slope that reaches 3,000 seconds for problems of size 3,000, that is linear programs. Linear programs have cubic complexity. It was good as an initial demonstration that compressed sensing has promise, but it's perhaps not very useful in the real world. What about these other algorithms? As I mentioned earlier, iterative hard thresholding, that's the fastest algorithm. When n is 10,000, it is 30 times faster than ours. That's pretty good. And we have these other competitors, COSAMP, Deanna's algorithm. And COSAMP is pretty good. Its slope is pretty good. But when we reach 10,000, we're almost as fast. And why? Because we use a sparse measurement matrix, and they are not making an assumption of sparsity. They're just doing matrix vector multiplication, quadratic time. Now, if I used the sparse matrix format in MATLAB, this would slightly improve their performance, but I wanted just to take their code unaltered. I did evaluate their performance with these sparse representations in the MATLAB. OK, what about the other algorithms? The COSAMP and the IHT are greedy. Well, the linear program is terrible. We just discussed that. And we have the GPSR, which is a fast implementation of the lasso. And for problems of size 10,000, we are 3-4 times slower, but we're getting there. Another point of interest is that for problems of size 10,000, our code, it might be n poly log n, but it runs for half an hour. That doesn't really make sense to any of you, does it? The problem is that in this n poly log n, I have a constant which requires me to run an FFT, a fast Fourier transform, for vectors of length approximately 500. And in the signal processing community, we are educated to believe that the FFT is very fast. But when you have a length 500 FFT, it takes quite a few microseconds. And when you take n poly log n times quite a few microseconds, it adds up to half an hour. This is not something, even with hardware implementations and parallel hardware and whatever, this needs more work. And now I'll tell you about fast.
Quick question.
Yes.
Just one quick question.
Yes.
If you go back to the previous slide, n is the length of the size of the signal?
The input, yes. N is the length of the input. Yes, Mutu.
So if I were to compare this to compressed sensing results, their running times are in terms of sparsity, like k poly log n, right? Where k is the sparsity. So these results are at least.
I will soon get to those algorithms. Okay, I will soon get to those algorithms. So again, half an hour, problem of size 10,000, speed it up in hardware, parallel, whatever. It'll still be too slow, and that's why we're. Yes, another question.
When you do the belief propagation,
yes,
you need to integrate into that the knowledge of the domain in which things are sparse.
You need to integrate that
Is that
every
where
statistical
FFTs
knowledge you have about the problem. Yes.
Is that where the FFTs come into it? Is evaluated?
No, the FFTs is because in the belief propagation, it requires convolution, and FFTs enable us to perform convolution very rapidly.
More rapidly than
Yeah.
the direct form
Yeah.
when it's sparse even?
Doing convolution the old-fashioned way takes a lot of computation,
Even when it's sparse?
even when it's sparse, yeah. More questions? So we have an interest in these very fast algorithms, as Mutu was pointing out, algorithms that are sublinear in the length n. And we will take a specific setting where, once again, I return to these perhaps colored boxes instead of blue, but my signal is precisely sparse. The white boxes are zeros. This is not what I told you before of a thing that could be any input, but this is a strictly sparse input where the white boxes are zeros. And I have neglected away the noise. Toy problem, but if you think about it at Google, you'll have your video data. You will have those n numbers, 10 million numbers per second. And out of those 10 million numbers, only 100,000 wavelet coefficients or whatever coefficients will be large. And the rest, you will force them to be 0. This might actually be a problem of relevance to Google, okay? How do we look at this problem? How do we solve it very fast? And I'll soon tell you how fast is fast. Here's a toy problem. Y, the measurements, equal phi, the measurement matrix, times the input, the vector x. And I have put question marks for the vector x. And I'm going to ask directed questions at the audience to help me solve the vector x. So one of the measurements is a 0. And I want to remind you that x is sparse. And I'm assuming that the non-sparse locations are real numbers and not ones or twos, and integers. And I did use, indeed, integers for this toy problem, but real numbers. So what does it mean? Can anybody tell me? Probably Mutu can tell us. What does it mean if a measurement is exactly 0 for this problem? Any volunteers? Mutu, what do you think?
You're muted, I think.
Any other volunteers here? Excuse me?
I'm just reading the slide, and I would conclude that the positions of the signal that you're adding up, they add up to 0.
Okay, so that is definitely correct. Any other guesses? Taking into account that. Yes? You're muting again.
Are you allowing negative numbers?
Excuse me?
You're allowing negative numbers?
I'm allowing negative numbers, but these are real numbers, a continuous distribution. Real numbers, and this is exactly 0. It's not quantized to 0, exactly 0. What do you think?
Oh, there's the second and third element.
Exactly. The second and third elements, which I am measuring, are 0. So now I'm going to put down these two will be 0. And I had a bipartite graph, and I am reducing the bipartite graph. Okay. Reducing the bipartite graph means these gray areas are no longer necessary. The first measurement, which was 0, is no longer necessary. The second and third columns, I just figured out that they correspond to zeros. They're no longer necessary. Okay? Graph reduction. Second observation is that we have these two measurements which are equal to 1. Once again, in my toy problem, I actually used integers. Think to yourself, I have identical measurements on real numbers. Identical measurements, no quantization. What does it mean? Identical measurements. Excuse me?
It's the second to last value.
Say that again?
The second to last. It's the second to last value that equals the second to last.
The second to last value, yes. So Michelle was pointing out that in the second row, it is picking up these two numbers. The third, or rather the fourth and the fifth number are being picked up. And in the next row, in the third row, we're picking up the first and the fifth. And the fifth is common to both. And the fifth will be equal to 1. The fifth number will be equal to 1. That's this question mark. And the first number will be 0. And the fourth will be 0. Once again, I've reduced the size of the graph. The last question. I have this very small system of equations left. The measurement equals 4. And I have 1 in the measurement matrix. What is the question mark? Wait, say that again? Okay, what's your guess?
She made a joke. She said 3.
3.9.
It is actually 3. Like some audiences would guess 4. But this is a trick question. What I forgot to tell you, and I forgot to tell you, by design, is that when I figured out that this guy that I'm measuring in the last row is a 1, I need to subtract it off. And this phase of the algorithm was actually discovered in the last several weeks by a 4th semester undergraduate. Okay? This last phase. These are the 3 parts of the algorithm. Very simple algorithm that you guys just redesigned by yourself. You redeveloped the algorithm. Earlier I was talking about 10,000 in half an hour. My 4th semester undergraduate, 100,000 in 15 seconds. Okay? Now, let's talk about the theoretical results. The number of non-zeros per row needs to be proportional to the length.
Sorry.
Yes.
Just, I must have missed the beginning. Why do you put 0 first? If it is negative number, they could be just pair of opposite numbers.
Because these come from a real-valued continuous distribution, and the probability that they will exactly be minus 1.732 and plus 1.732, the probability of that is 0. Because we have noiseless measurements, okay? So when you have noiseless measurements, the probability of things summing up to 0 by mistake is 0. Now, when you have only 8 bits on your measurements, you have a likelihood of making mistakes. But when you have 64 bits, everything is going to be fine.
Yeah, with 1 bit of error on
Again, this is
measurement,
this is a toy problem. The input is exactly sparse,
that's kind
and
of the fundamental initiation of the algorithm, removing the zeros. So
but once again, like a continuous distribution for the input, for the non-zeros. If it's continuous, the probability that you'll have multiple numbers summing up to exactly 0, it's not going to happen in practice. Okay? Again, 2 to the 64 representation levels. What's the probability?
If you start making a little bit of mistake, even 1 bit at the very early stage, with all the numerical accumulation of error we are about to make in the inference, kind of fear will blow up, and that's kind of the fundamental starting point of that.
So the real question is, how many bits do you store your measurements at?
Yeah. What's the,
And
so the 0 price, how much bits are you willing to discard?
So if Google will do this type of stuff with 8 bits, maybe occasionally you will have mistakes. With 16 bits, you will rarely have mistakes. With 32 bits, it'll almost never happen. Okay.
All right.
Okay. Now, theoretical results. The number of non-zeros per row needs to be the length proportional to the length of the input divided by the number of blue boxes. And the number of measurements needs to be the number of blue boxes times some log factor. As I said before, typically 5 times the number of blue boxes. So instead of 100,000 numbers that Michelle would send for video, maybe 500,000 numbers. But our encoder is n log n, and our decoder is somewhat larger than k, sometimes some log terms. And Muthu would probably notice that this is sublinear in n. K, the number of blue boxes, is much smaller than n. But I have a caveat here. This is the actual graph reduction step. And it so happens that setting up the data structure takes n log n. Setting up the data structure requires to have locations for each of the red locations in the matrix. Now, if in my cell phone I would have this algorithm pre-programmed and the data structure would be set up, it would be n log n. I'm sorry, if it's already set up, it would be k polylog something. If I need to redo this data structure from scratch, it is n log n. And this is a subtle point, but we need to be fair with the community. And despite the n log n, problems of size 100,000 run in 15 seconds. Now, why do I think this is of particular interest to Google? Because Google obviously does distributed content distribution. You have servers all over the world. And for my problem of 100,000, where I have 5,000 blue boxes, if you give me 18, 19,000 measurements, I will be able to recover the problem. It doesn't matter what servers in the world will send me those 18,000 numbers. I will be able to solve this problem. Some of your servers will crash. Some of the TCP/IP will not arrive on time. If you get me 18,000 numbers a second, I will give you the 100,000. This is a MATLAB implementation. It can be improved in C. I'm sure that your programmers are even better than my brilliant 4th semester undergraduate. Now, once again, toy problem, strictly sparse, noiseless measurements. Now I have a third topic on distributed compressed sensing, which I indicated to Michelle that I will skip. If people will be interested, we can do that offline later. But let us go to the part of the talk which kind of gets back to what might interest you. This is not just about compressed sensing. This is about linear measurement systems. We're interested in a unified theory for all kinds of different systems that measure things linearly, and not just the theory, but also fast algorithms.
I'm sorry,
Mutu.
sorry, the other one, but I want to ask you a question which I'm a little bit confused about. Maybe you can answer me later by email. But
Yeah.
this is, I mean, we had results for 3 years on K-polygon measurements, and so can you tell me sort of, maybe later by email or something, sort of what is the new bound in this theorem? I should be looking at the theorem's focus. I mean, compressed sensing, we know we can do it K-log and over K measurements. We can even do it in decoding in K polylog in time. Is it the poly that's going to change? Or
the contribution of our algorithm, first of all, Deanna and I are extending it to noise. And secondly, as I mentioned, a very simple algorithm. And that's why we find it very pleasing. You know,
But the way we deal with them in streaming literature is just take group testing, and the algorithms are very simple to decode, right? You don't use propagation, you don't use...
No. Our algorithm...
Group testing.
No, absolutely. This algorithm is this algorithm, no belief propagation, no nothing. I described the entire algorithm.
Right, but likewise, I could in one slide describe the combinatorial group testing based decoding. So I don't know what the comparison is. Maybe in terms of log factors, I'm a little confused about the comparison.
The log factors are a bit different. They might be competitive. I'm not really sure. Let's take this offline.
Okay, good.
Okay. So going back.
And I want to be sure I got the main picture.
Yeah. No. All of these results are competitive with each other. Like there are plenty of fast algorithms. And as I mentioned, just setting up the data structure is n log n. I have no need to lie about that. If it's pre-programmed, it's sublinear in n. If it's not pre-programmed, you need to set up the data structure. Now, linear measurements. I was with a hedge fund for 1.5 years. And let me describe approximately how numerous hedge funds are trying to predict stock prices. So in their world, they have, Fama and French in the early 90s described a 3-factor model where you have different factors that drive thousands of stocks, the returns of thousands of stocks. Let's say the stock market index goes up by 1% today. There will be some companies that on average move more aggressively than the market. All other things being equal, they will move 1.5 times faster, so 1.5%. Other companies are kind of, relaxed companies. Don't want to give any examples, but let's say they only move 0.5%, all other things being equal. That's one factor. Other factors are relative to earnings. Are you an expensive company or a cheap company? For example, I think it's well understood in this room that 2 years ago, relative to earnings, Google was an expensive company. But that's because Google grows very rapidly. So there was a reason for that. There was a reason why Google was expensive. So there are numerous factors that are used to attempt to predict stock prices. And the way how it works, you have X, the input. And the input here, which you are trying to estimate, is the factor returns. How much each of these factors drives the stock prices. The matrix phi is basically every row of the matrix corresponds to one stock in your training data in the past. So many months of data, or perhaps many seconds of data for fast trading firms, for many, many companies. So this could be millions of numbers, why? Or it could be gigabytes or terabytes. And based on this training data, and you know the exposure, you can compute the exposure of these companies to the different factors, you want to estimate X. Now, of course, you have, I would not call it noise, I would call it the unmodeled portion of the stock market, and that is Z. Now, in their problem, the unmodeled portion is typically very large. Very difficult to predict the stock market. If it was easy, any of us could make 100% a year. Now, let's compare compressed sensing to finance. In finance, if you can compute those factor returns then you can predict the future. If you compute them, you predict the future, you invest on it, you make money for your clients, everybody's happy. So the goal is to estimate the factor returns x conditioned on knowledge of the exposures phi and the data, the past training data y. We have compressed sensing, we have finance. In compressed sensing, y is very short. In finance, y, the training data, is very long. In compressed sensing, x, the input, is very long but sparse. In finance, x, the number of factors, is perhaps a few dozen. In compressed sensing, it is implicitly assumed that the noise is minor. In finance, the unmodeled portion of the data is massive. And that's why, although you have a lot of data, it's very difficult to predict the market. Because the unmodeled portion of the data, of the past training data, stock returns, you have a lot that doesn't really sit inside your model. Now, compressed sensing, of course, we talked about that. Finance, not only is the data noisy, and because of that you need a lot of measurement, you have nonlinearities here. You have stock market investors whose behavior is changing over time. This is a non-stationary environment. Complicated problem. And that said, we understand that compressed sensing is a linear measurement system. Finance, we have some people who use linear models. Medical imaging, tomography, it can be approximated linearly. Same with seismic imaging in the oil industry. They attempt to see what's underground using things that can be approximated by linear measurements. Google does information retrieval. What I'm getting at is that in these different areas of science and engineering, we have linear measurement systems. The goals are fairly common. We want to minimize resources. Once again, speed of the analog to digital converter, cost of the hardware, power, bits, you name it. We want robustness to imprecisions in our model and robustness to noise. And we also want things to run quickly. Now, some people call these inverse problems. I view this as a slightly different information theoretic type of problem. But where I want to go to is a theory and a way how to really, really rapidly process, extract information from these types of linear measurements. Thank you very much. Questions?
I think we're somewhat over time, but if folks want to head with us to lunch, that would be great too.
OK. Anybody who wants to ask can definitely join us for lunch, I imagine.
Just a quick question.
Yeah.
Probably not going to make it. Just how does this could extend to nonlinear compressed sensing? Because it's all about matrices and.
You could, I think you could use Taylor approximations as some of the columns. If you had, via Taylor approximation, some of the columns would be measuring the square of something. I think that that could be done to do some nonlinearity. I've not really thought about that in detail. But you know, when I say Taylor approximation, that gets you thinking. Yeah.
The content distribution aspect, how does that compare with fountain codes?
I think that we need more measurements. I don't really know. I'm aware of fountain codes. I haven't gone into the details. I don't know the details.